Hello there and welcome to my channel on chemistry lessons. At the moment we do predominantly focus on A-level chemistry lessons and they are designed to be full lesson videos. So please make sure you subscribe and you like to make sure you don't miss out on future videos. I do aim eventually to cover the full A-level specification. If you think there are any gaps, please let me know and I'll ensure that I fill them for you. So hopefully you find it useful and good luck. This is an alkenes lesson and it's the second lesson in a series of 3. The previous lesson looked at the bonding in alkenes, so looking at that double bond, and this lesson is going to look at the reactions of alkenes. So looking at the specification then, we start to look at a new mechanism called electrophilic addition. So in a previous topic on haloalkanes, you'll have seen nucleophilic substitution. And here we see the term electrophilic addition, so a very different mechanism here. So you can see there we've got 3 electrophiles to look at, HBr, H2SO4 and Br2. And moving on from that, how bromine is used as a test for unsaturation. Probably have that knowledge already from GCSE, the idea that bromine water goes from orange-brown to colourless in the presence of a carbon-carbon double bond, but we'll recap that again. And you can see this is where it gets a little complicated, is looking at the major and minor products, because we can get a mixture of products here, particularly for unsymmetrical alkenes. So we're going to look at the mechanisms and look at those major minor products. Let's start off with some language then. So we've seen in previous topic haloalkanes, we've used the term nucleophile. And if we're asked to define what a nucleophile is, we can call it an electron pair donor. So it donates a pair of electrons. Now the good news is, electrophile is quite literally the opposite. So what is an electrophile? It will accept a pair of electrons. There we go. So if we're asked for a definition, accepts a pair of electrons. Now an electrophile is usually positively charged or slightly positively charged, just as we've seen nucleophiles tended to be negative or slightly negative because they're electron rich. They'll donate a pair of electrons. An electrophile will attract electrons and is positive, slightly positive, but the key definition is accepts a pair of electrons, and a nucleophile donates a pair of electrons. And now let's compare addition to substitution then. So with substitution reactions, we are, as the name suggests, we are swapping, we are substituting one substance for something else. So a straightforward substitution. Addition, we are adding to that double bond. We are not swapping anything, we are adding something. So as we've seen with alkenes having a double bond, that double bond can break and we can add a substance to it. So that's an addition. So nothing will be lost. We are adding something to it. We are adding an electrophile. So that's why we call this an electrophilic addition. So why do alkenes undergo electrophilic addition? Well, let's have a reminder of this double bond. So alkenes, the functional group in an alkene is this double bond. That's our functional group. Now, from video 1, this region, this double bond is electron rich. We've got 4 electrons, we've got 2 pairs of electrons, so we'd call that electron rich, which means it's got a high density of electrons, which will be attractive to an electrophile. Electrophiles are going to be attracted to that area of electron density. And the reason they'll undergo addition is because it's unsaturated. We can break the double bond. So that pi bond can break. The sigma bond can't. So alkenes will undergo electrophilic addition because the pi bond can break and they are attractive to electrophiles due to the area of high electron density. So what does our specification want us to look at in terms of electrophiles? We've got 3 electrophiles and it's very clearly shown in the spec up here. We're going to look at the electrophile HBr. We'll look at the electrophile H2SO4. Now we do need to know the structure of this. It's sulfuric acid. It's sulfur with 2 double bonded 2 oxygens and a single bond OH. and again a single bond OH. So that is the structure for sulfuric acid, H2SO4. We do need to know that structure. And also then the third electrophile is Br2. So those are our 3 electrophiles. So what I'm going to show on each of them is their polar bond. So HBr is highly polar. And there we have there. Bromine is more electronegative. That's highly polar. And in H2SO4, these 2 H's are delta plus and can act as the electrophile. So we can see here we've got electrophile here and here. It doesn't matter which one we pick on sulfuric acid. Look, there are 2. So we can just pick one or the other. The Br2 is a little more difficult to understand because it is in fact non-polar. So when we do this in a couple of slides time, I'll explain how this is able to act as an electrophile, because looking at it, it's non-polar. It doesn't really look like it should be an electrophile. So we'll look at that in a couple of slides. Let's start with the first one then, HBr. So I'm going to draw just a very straightforward alkene. There's ethene. We will look at more complex ones later when we start looking at major and minor products, but there's a very straightforward and simple alkene, ethene. I'm purposely drawing the delta positive H closer to that double bond because it's going to be this delta H, this H delta plus that's going to be attracted to this area of electron density. So these 2 are going to be attracted to each other, not the other way around. Okay, it's not going to be the Br minus. That would in fact repel. So what happens is the pi bond, so go from the pi bond to the hydrogen, and then the HBr bond breaks, being very, very clear and specific with my movement of electrons there. Remember, a curly arrow shows the movement of 2 electrons, the movement of a pair of electrons. So what we have now is the pi bond has broken. It's now just a single bond. The H is now bonded to one of the carbons. It doesn't matter at this point which one I pick because it would be the same either way around. So it doesn't matter which one I show the hydrogen bonded to, but the other carbon will be positively charged and we'll have a Br minus. So that's the first step in the mechanism. The second step, this Br minus, this pair of electrons from the Br minus will form a bond with that carbon there. And we're going to end up with bromo ethane. So what we've just done there is we've just made a haloalkane from an alkene. And had we done it the other way around and had the hydrogen bonding to this carbon and having the other carbon as a positive, had we done it that way around, we'd have just had the bromine in this position and the hydrogen in this position, which would have left us with the exact same substance, bromo ethane. Just draw those back in for you there. So that's bromo ethane. Now the good news is this is exactly the same mechanism. We have exactly the same mechanism, and it's exactly the same in all 3 cases. In fact, the electrophilic addition mechanism is the same every time. It's just this one feels a bit more awkward because we've got to draw out the sulfuric acid, which does cause some people some stress. But sulfuric acid, there we go. And I'm going to draw my polar bond to show the electrophile. And then the same thing happens, the pi bond to the H, that bond breaks. If you hear me say from the pi bond, it doesn't matter where I'm just coming from the double bond. It doesn't have to be any one of the 2 in particular. It just has to be from the double bond. So what do we have left here? Now I'm going to draw, just because I can, I'm going to draw the positive charge on the other carbon because it doesn't matter, because it is perfectly symmetrical, so it won't have any impact whatsoever. It only has an impact if it was unsymmetrical, and that's what we're going to look at a little bit later, some more complex or complicated examples. So I'm just following through the exact same mechanism. Look, whether it's HBr or H2SO4, it's exactly the same. Here we go, It just looks a bit more impressive when I draw my product out because it looks more complicated. But as long as you know the structure for sulfuric acid, it's straightforward. So what I'm doing now, there we go. Now, you don't come across this. This isn't necessarily a functional group that we're familiar with. It's the only time we'll see this in the whole of A-level chemistry. And these are called alkyl hydrogen sulfate. So it's alkyl hydrogen sulfate. In this case, it would be ethyl hydrogen sulfate because our alkyl group is an ethyl group. So this would be called ethyl hydrogen sulfate. Okay, so let's look at bromine as an electrophile then, because I have said that a bromine molecule is non-polar. So how does it act as an electrophile? Well, what happens here is, due to the fact that this area here is a high electron density, there's a large area of negative charge, what happens is this pi bond, area of electron density, causes the electrons within this bond to be repelled and pushed this way. Electrons are negatively charged. This area here is a high negative charge, or high area of electron density anyway. It's high, there's lots of negative charge there. So it will force these two electrons to be repelled, and we end up with a temporary dipole, where we have that situation going on. So this double bond, the pi bond, the alkene bond, has caused a temporary dipole in the bromine molecule. And then we just go through the same mechanism that we've seen. There we go. Autopilot now. So the Br, it doesn't matter which one I attach it to because it's perfectly symmetrical. We have our intermediate here, the carbon with a positive charge. And then the last step, you guessed it, is this. Notice how the arrow is pointing to the carbon and not the positive charge. It is important that we get our curly arrows precise and in the right place. So what we've just made here is 1,2-dibromoethane. And this is our test for an alkene, because this substance here, bromine, this is an orange-brown liquid. So it's an orange-brown solution. And if it reacts, it's gone. It's not there anymore. So this becomes colourless. So if there was an alkene bond present, your bromine solution reacts and decolorizes. So it goes from an orange-brown solution to a colourless solution. That is your test for saturation or unsaturation. If a double bond is present, it will decolorize. If it isn't, it won't. Okay, so I suggested earlier that it does get a little bit more complicated if the alkene is more complex and unsymmetrical. So let me draw an unsymmetrical alkene. There we go. So that's but-1-ene. And let's have a look at what happens in this case then. So let me just draw this out. There's my but-1-ene. What happens now if we add something like HBr? So I'll stick with HBr simply because it's easier to draw the mechanism out. Now, if it was something like Br2, it doesn't really matter because you're just going to end up with the bromine on both of them anyway. So you would end up with the 1,2-dibromo. But if we're looking at HBr or H2SO4, let's see what happens. So the first step of the mechanism is still the same. There we go. But I've got two options here. I could put the hydrogen on the first carbon, like this, and have a positive charge on the second carbon. Just finish the rest of the molecule. So I could do that. That's option 1. Or I could have put the hydrogen on the second carbon and have the positive charge on the first carbon. So those are my two possibilities here. And that's why we get a mixture of products in some cases. Because it does matter which way around I do it all of a sudden. If I went for the first option, option A, I'd end up making 2 bromo butane, and if I went through option B, I would make 1 bromo butane. So how do we decide? Is it simply a 50-50 mixture, or does it prefer one over the other? Now, the specification did say the major and minor product, so actually in some cases it does favour one over the other, and I can see from what I understand of chemistry that option A is most likely. So option A would be the major product, option B would lead to the minor product, and I'm going to explain that now. So those 2 intermediates that we saw are classed as carbocations. So I'm not going to draw all the hydrogens out, I'll just do a quick sketch. So one of my options was the positive charge here, and the other option was the positive charge on the first carbon. So those were your 2 options. Now, when you have a carbon with a positive charge, it's classed as a carbocation. So when you see the term carbocation, it means it's a carbon with a positive charge. So these are both examples of carbocations, and they are classed as carbocation intermediates because they are intermediates in this mechanism. Now, the first one, or the one on the left, this is classed as a secondary carbocation, and that's because there are 2 carbons bonded to the carbon that's positive. The one on the right is classed as a primary carbocation because the carbon that's positive only has 1 other carbon bonded to it. So there is a third type of carbocation, which would be a tertiary carbocation when it's got 3 carbons bonded to it. Now, these carbon groups or R groups, notice how I'm drawing arrows. A carbon group or an R group, often referred to. An R group is electron pushing or electron donating. So it slightly stabilizes the charge, making it more stable. So the tertiary carbocation, because it's got 3 R groups or 3 carbon groups, 3 alkyl groups, it's more stable than the secondary that only has 2 R groups. And a secondary is more stable than a primary because the primary only has 1 electron donating R group. So the most stable is a tertiary, followed by the secondary, followed by the primary. So let's go back to this example then where we said we had those 2 possibilities, A and B. So the mechanism is the same for that first step, as you can see, but we've got those 2 options now where we can put the hydrogen on the first carbon and have the second carbon with a positive charge, or we can put the hydrogen on the second carbon and the positive charge on the first, which was option B. Now let's look at these carbocation intermediates. Now the one on the left is classed as a secondary carbocation because it's got 2 R groups. The one on the right is classified as a primary carbocation because it has 1 R group. Now we know that the secondary is more stable than the primary because it's got 2 electron donating R groups. Therefore, mechanism A will be the major product because it's the most stable intermediate, and option B with the least stable intermediate will cause our minor product. Now I'm not going to draw the final products out, but the one on the left is the major, which is the 2 bromo butane. The one on the right, 1 bromo butane, it's the minor, and we need to be able to clearly explain why in the exam. So we're clearly explaining that A is the major, the 2 bromo butane is the major product because the carbocation intermediate for that mechanism is a secondary carbocation compared to the primary carbocation. Secondary carbocations are more stable because they have 2 electron donating R groups, leading to the major product. That brings this lesson to an end then. So go away and practice as many mechanisms as you possibly can for alkenes, and they do get very, very repetitive and straightforward. Good luck. Don't forget to subscribe and like.